Hello. Today we're going to introduce one more of your conic sections when we talk about hyperbolas. And you're going to find that hyperbolas look different than the other conic section, a bit different than some of the other conic sections like ellipses and circles. But the way they're defined and the way that the equations are derived is done in a somewhat similar manner. All right, so let's first define what a hyperbola is. Hyperbola, the set of all points in a plane such that the absolute value of the difference of the distances from two fixed points is constant. Don't worry, I'm going to draw a picture in just a minute to show what this show what this means. The two fixed points are the foci of the hyperbola. Okay, so let's draw a little picture. Pictures can speak 1,000 words, right? Or I like to say graphs can speak infinite solutions, if you want to adapt that to mathematics. So let's look at our grid, XY system. And let's center our hyperbola at the origin for this. Okay, and I'm just going to do a really quick rough sketch, much in the same kind of pattern as what you might see in your book. And you'll find that the hyperbola looks like two parabolas facing away from each other. That's kind of like what it looks like, but it's its own thing. And again, this is not drawn to scale. I'm just trying to give you an idea about what this definition means. Okay, so this is centered at the origin. The F and F primed are vertices. We're going to go ahead and label F that as a C, 0 for the ordered pair, and F primed we're going to say is negative C, 0. And then for the vertices, let me switch back to blue. Vertices, we're going to have a V primed, and we're going to say that that's at negative A, 0, and we're going to have a V, and we'll say that that's at A, 0. And then again, the blue curves, those together make your hyperbola. The hyperbola has both of those curves, those two curves there. Those blue curves, that's the set of all points in a plane, such as the absolute value of the difference of the distances from two fixed points is constant. Okay, so the foci are those two fixed points. So let me draw just a random P point. Call that point P. Some point on the hyperbola. It can be anywhere on the hyperbola. But the definition is looking at the distances that you see in purple. And it's saying that those distances from any point P, if you subtracted them and then just did the absolute value, in other words, made sure you just took the positive outcome of that, then that's going to be constant. So no matter what point you pick on the hyperbola, on either curve, you're going to be able to do that with your distances to the foci. Okay, and then using that fact, we can then derive an equation for this hyperbola. Okay, so we know then by the definition that the distance is from any point P. So, you know, for convenience sake, let's use the vertices. I mean, you could use P, but X and Y, I mean, it could be any point on there according to the definition. So let's, for convenience, use the vertices. So distance from vertex V to F primed subtracted with distance vertex V to F. We can work on that and come up with something. Distance from vertex V to F primed, that is C plus A. Because you have that distance C from the origin to F primed, and then you have the distance A from the origin to V. And then if you subtract that with the distance from V to F, so from the origin to V is A, from the origin to F is C. So you can subtract C and A to see what that little distance is between them, between V and F. If you work that out, you get C plus A minus C plus A, so you get 2A. And since we can use V, you know, you can use that interchangeably with P, because, you know, as long as it works for V, it's got to work for any point P there on that, according to the definition. So we could say, too, that the absolute value of the distance from any point P to F primed minus the distance from P to F has to equal 2A. Now I'm going to kind of skip ahead. Like when we did an ellipse, I referred you to your book to look up some algebra. You can perform some very similar algebra using your distance formula and then working it out except using now your hyperbola graph and information. And when you do, you end up with this equation. So it's in a similar manner to getting the equation for an ellipse, but this is for a hyperbola. All right. And then I know in the ellipse, it was pretty straightforward how to replace the c squared, like in this case, c squared minus a squared, like something like that with the ellipse. It was pretty easy to figure out it was pretty straightforward to figure out how to replace that and clean this up. But the hyperbola, it actually involves going into a different kind of geometry, and we're not equipped to do that right now. So just trust me that b squared equals c squared minus a squared for the hyperbola. You can take some more advanced geometry classes and you'll get into why. So then you can clean up that equation and say for hyperbola centered at the origin, x squared over a squared minus y squared over b squared equals 1. And you might notice the equation looks kind of similar to that of an ellipse. But there's one key difference in just glancing at the equation, and that you see a minus sign instead of a plus sign. There's a lot more differences when we go to actually graph, but just be aware, like try to keep that straight when you're trying to identify the equation and what it goes to. The ellipse and the hyperbola look very similar, but the ellipse has the plus sign while the hyperbola has the minus sign. Okay, so then once we have that equation, again, this is going to be centered at the origin at 0, 0. A little later, we'll look at the equation if it's centered elsewhere. But yeah, if y equals 0, then the intercepts are plus or minus a comma 0. You could plug in 0 for y. You have x squared over a squared equals 1, so x squared equals a squared, so x equals plus or minus a. Now, if x equals 0, there's no real number solutions. So that tells us that there's no y-intercepts in this situation. This is for the hyperbola centered at 0, 0. Now for sketching the hyperbola, we've developed some aids. The aids are not actually part of the graph, but they help us to figure out where to sketch it. And we use kind of the concept of limits, or if you'd rather, you can think about asymptotes. We can take the equation, and go through and solve for y. You can look in your book how to do that, page 1015. But when you solve for y, you get y equals plus or minus b over a square roots of x squared minus a squared. So if you're not sure how to work that out, you can look in the book. It's some basic algebra. And we can look at this and realize something. When x squared is really big compared to a squared, then the difference x squared minus a squared is going to be closer to x squared. Like if you think about it, like let's say you're subtracting numbers. If the numbers are close together, then the result's not going to be that necessarily that close to the numbers. So like if you're subtracting 100 and 99, the result's 1. That's not very close to 100 or 99. But if you spread it out, like let's say you did 100 minus 1, you get 99. 99 is pretty close to 100. So with that in mind, like this, the further apart they get, the closer and closer that the points in the equation are going to get to y equals plus or minus b over a x. So for x larger than a, you're going to get close to, but not touch it, that. So in your book, they'll say, as the absolute value of x increases without bound, points of x squared over a squared minus y squared over b squared equals 1 approach the lines. They don't touch them, it's asymptotes, but they approach the lines. Y equals plus or minus b over a x. So these are going to be asymptotes and are useful for sketching. Okay, so let's just jump right into it. How about we go ahead and start working on graphing a lovely hyperbola. When we go to sketch the graph, they're going to ask us to not only graph it, but they'll say tell us the coordinates of the vertices and the foci, and give the domain and range. All that good stuff that we've been doing. So let's say you've got x squared over 4 minus y squared over 25 equals 1. Okay, so a squared's underneath the x squared. So a squared's 4, we know b squared's 25. So we're going to use 2 for a and 5 for b. And then according to hyperbola, our standard for the c, c squared equals a squared plus b squared. So c squared, which is 4 plus 25, so we're going to get 29. So c, we're going to be dealing with the square root of 29. All right, so that a underneath the x tells us how many we need to go out as far as the x-axis, the horizontal axis, and the 25 or 5 under y, the b equals 5, tells us how far along the y-axis we need to go when we're trying to graph this. So let's see here. Trying to figure out on my grid here where I want to put it, because the foci are going to be kind of far out. Yeah. All right, I'm going to have to like double up. Okay, so that's what I'll do. It'll work out. All right, we're going to go by 2s on the grid, so I'll draw, in between. All the little things I'm marking are going to be by 1s. I was just looking at the pre-done grid in the background. That's basically by 2s, you might notice. But my little marks are by 1s. Okay, so what we do is we can draw ourselves like this invisible rectangle. We go 2, like 0, 0 is the center. We go 2 to the right, 2 to the left, because of the A. We go 5 up and 5 down, because of the B. And we can draw a little rectangle, like a dashed rectangle, just as a guide. It helps. And the lines that are basically make up the diagonals of this rectangle that go through the center, those are those lovely asymptotes we were talking about. Y equals plus or minus b over a, so 5 halves x. Yeah, so either way, so you have your asymptotes. So for this one, your vertices are at plus or minus 2, 0. Because A being 2. So that's these 2 points on your rectangle. And then your curves are going to open up and get closer and closer to those asymptotes, but never actually touch them. So the stuff in the dotted lines isn't actually part of the graph. That's guides. I mean, unless you think about the asymptotes, they are technically a part of this, but they're guides to help you figure out where to draw the curves and like how wide to make them and that kind of thing. Yeah, so the asymptotes were here. Vertices, the foci are at plus or minus square root of 29, 0, which the square root of 29 is around 5.39. So that's where I was thinking when I was trying to figure out how far to make my grid. So your foci are out there. So you can pick any point you want on the parabola, or on the hyperbola, I keep saying that, on the hyperbola that we just drew. And if you look at those 2 foci and look at the distances from any point on the hyperbola to those 2 foci, you can subtract the distances and take the absolute value of that. And it's going to be the same no matter what point you pick on your hyperbola to those 2 foci. All right, so we found the asymptotes, we found the vertices and the foci, and then domain and range. Okay, so domain. Well, this graph goes from negative infinity up to, like, from the left to right is domain, x's. So from negative infinity up to that vertex at negative 2, it includes that, so bracket. Then there's that big gap. And then it picks up again at the other vertex at 2 and goes to the right forever. So 2 to infinity. And then for range, Well, these curves both go forever down and forever up. So negative infinity to infinity for the range. So there you go. All right, you might in your mind be thinking like, then what do these hyperbola? I see that one opens to the right and one opens to the left, but do they ever open like up and down? And yes, they do. The equation looks a little different. When that happens, your A's and B's will still be in the same places, but your X's and Y's will be switched. Okay, so let's look at an example where that happens. Okay, let's say you have something like y squared over 64 minus x squared over 4 equals 1. So then seeing the y first sends up that little flag of, oh, okay, so this hyperbola has to open up and open down. But the a is still going to be underneath in the first fraction there. So a squared is 64, a is 8. B squared is 4, b is 2. But now the a is associated with y and the b is associated with x. So it switches things up for us. C squared is going to be the 64 plus 4. So a squared plus b squared, which is 68. So for C, we're looking at, square root of 68, or 2 square roots of 17, which is approximately 8.25. So our vertices are still associated with A, except now it's along the y-axis. So it's going to be 0, comma, plus or minus 8 for our vertices, because it's going to be along the y-axis now instead of the x-axis. And then our foci also now along the y-axis. So it's going to be 0, comma, plus or minus 2 square roots of 17. And then our asymptotes, those get switched up. It's going to be y equals plus or minus a over b x. So we got plus or minus 8 over 2 x. So plus or minus 4x equals our y for our asymptotes. So yeah, it looks a little different. Still rise over run. Asymptotes are equations of lines, so you're still looking at rise over run. And since A now is associated with the y-axis, that's your rise. And B being associated with your x-axis, that's your run. All right. So let's do this. You know what, let me shift this graph down a bit. Sorry about that. Notorious for running out of space. I think that'll do. All right. Okay, so if A is 8, then vertex, I got to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. And I got to go down 8 from the origin. So there we go. And then B was 2. So I'm going to go right 2 and left 2. I can draw my drawing the little dotted rectangle helps. And once you draw the diagonals through the center, you'll have your asymptotes. rise over run. So, you know, up 4 over 1, up 4 over 1. Or down 4, left 1, down 4, left 1. You end up there. So one of the asymptotes is here. And then the other direction is negative. So same idea, except downhill. Okay, so there's your asymptotes. So your hyperbola is going to be situated up here, holding water, and then down here, dumping out water. And that's what you need for sketching that graph. Your domain in this one will be negative infinity to infinity. Because notice the little curves, they extend forever, both of them extend forever to the left and forever to the right. And then your range this time is limited. From below, you can go from negative infinity up to -8, and it includes that point. Union, and then it picks up again at +8 and goes up to infinity. So there's your domain and range. And your foci, around 8.25, so 2, 4, 6, 8. So really close to those vertices. My pen's so thick I can't even quite differentiate between a vertex and where my foci would go, but pretty close. All right, what are we going to look at next? I'm not going to graph this one, but I just want to point out something. Let's say your equation doesn't look like it's in standard form. Like, let's say they give you something like 16y squared minus 25x squared equals 400, which we faced this back when we were doing the ellipses. Now remember, you want the equation to equal 1. So you can always divide everything through by 400 and see where that takes you. So 16 over 400, that's going to reduce. So you end up with y squared over 25. Right? Yep. And then minus, and then x squared. 25 goes into 400. And that's 16 times, and that equals 1. So you'll have now your classic hyperbola centered at 0, 0. You have that minus sign in the middle. It tells you it's the hyperbola with this y squared over 25, x squared over 16 equals 1. So like in this case, your a is 5, your b is 4. And this is one of the ones that's going to open up and open down. So I'll leave that to you to graph, but just wanted to show you like what to do if the equation is not in that standard form yet. Okay, what if it's not situated at the origin? I know that's your next question. Well, you got two possibilities, but you're going to have your center, once again, they like to use HK. And the equation's going to be a lot like what we were seeing before. Remember for this one, c squared equals a squared plus b squared. And you're going to have your differences in like the way it's facing, depending on how the equation's set up. If you have the equation like this, where your x is over in that first fraction before the subtraction, notice again, still a is in the first fraction, b is in the second one, but it all depends on what's happening with that x and that y. This one has that parabola. It's going to open left and open right. And then HK is going to be that center. So you have to consider that when you're working on it. This one has a horizontal transverse axis. You're going to have those vertices there along that axis, where the horizontal axis, it goes through HK. And then your foci are going to be somewhere along that axis too. Okay, but you still have your rectangle and everything, just now it's centered differently. So the A and B are still going to tell you about how big to draw the rectangle and like how to draw your lines. But now things are shifted. So now your vertices are going to be H plus or minus A, comma, K. So that A tells you like how far left or how far right from H you're going to get your vertices. And then your foci, still using C, H plus or minus C, comma, K. So from that center, HK, you go to the right C units, left C units to get your foci. And then the asymptotes, those lines have been shifted depending on where HK is located. So you're still going to start out with that slope, plus and minus B over A, and then X minus H plus K. So H is how far it's shifted left or right. K is how far it's shifted, up or down, depending on whether there's a positive, negative, etc. And then just like before, swap the X and Y, and then you've got the ones that open up and open down. So like if you have Y minus K squared over A squared, so the K is still associated with the Y, the H is still going to be associated with the X. Because those are coordinates. H comma K, so H, X, Y coordinates. So those stay together, but now the Y minus K squared is going to be over the A squared. So then that switches things up a bit here. So you have your center still HK. You'll have vertices and foci now along a vertical transverse axis. So your vertices this time are going to be H comma K plus or minus A, and your foci are going to be a H comma K plus or minus C. And then your asymptotes, you're going to have Y equals, remember for this one it switches it, you have A over B because now A is associated with your Y or your rise, B is associated with X or your run, and then X minus H plus K. So it's equation of a line, but now you're shifted according to that center. Okay, so let's graph one. Let's say we have something like X minus 2 squared over 16 minus Y plus 4 squared equals 1. Okay, if I don't see a 1 in a fraction, I like to write it just to keep in mind that it's there. So I'm going to put the Y plus 4 squared over 1. That'll help me to keep track of what's going on here. So my center, HK, is at 2 comma negative 4. Then my A is 4. Square root of 16 is 4. My B is 1. So C squared is 16 plus 1, or 17. So C is the square root of 17. I'm not sure what that, I didn't write down what that is. Let me real quickly punch that into my calculator. 17 square root is around 4.1. So helpful to know. Okay. And then my asymptotes they're going to be at y equals, so this is, since the x's came first, this one opens left and opens right. So y equals plus or minus 1/4. So plus or minus b over a, 1/4. Then x minus 2, parentheses, and then minus 4. Because it's normally x minus h plus k. So the x coordinate has the opposite sign, y coordinate has the same sign. All right. Let's figure this out now. So 1, 2, 1, 2, 3, 4. So if my center's at 2, -4, I know it's going to be right there. But I'm going to need a lot more than that. All right, if a is 4 and b is 1, well, a is 4 means I need to go 4 to the right and 4 to the left for my vertices. That tells me where that part of the rectangle is going to go to. And if b is 1, I go up 1 and down 1 from the center. So it'll be like that. My asymptotes. Using those diagonals of that rectangle. And then I know this opens left and right, so then I can sketch my little curves for my hyperbola. So there they go. All right, then my foci would be 4.1 from that center point, really close to the hyperbola. It's hard to draw it. It would be so close that it would, right now, if I drew it, it would look like it's on top. So, but still, you got your foci out there. All right, I think that covers that. Oh, domain and range. Domain, it would go from -infinity to -2 bracket, union 6 with a bracket to infinity. And then my range, we go -infinity to +infinity. All right, so I think we've covered that now. Yeah, if you want the actual coordinates of things, your vertices. So you end up taking 2, you add 4 to it, and you get 6, -4 for one of the vertices. And you subtract 4 from it, and you get -2, -4 for the other vertex. And then for foci, you're taking 2 plus square root of 17, -4, and you're taking 2 minus square root of 17, -4. That's how you get your foci. Now I think I've about covered all of it. Yep. Okay. So there you go. So that's how you deal with what if it's centered elsewhere with HK. Okay, 2 more things, then we'll be done. What if you have a parabola or hyperbola? I keep saying that. Hyperbola, that the equation's not in standard form and it's also not centered at 0, 0. Like we did one earlier where the equation was centered at 0, 0. But what if it's not? What if you have 9y squared minus 90y minus 25x squared plus 150x equals 900? What if you want to just get that equation into that standard form? Well, if you guessed that we're going to have to complete the square, you guessed correctly. Let's first factor out things in where we have the common variables. So like the y's, let's factor out a 9 for those two. leave a little space. And for the x's, let's factor out a minus 25 for those two. Leave a little space. That's going to equal 900. I haven't added or subtracted anything new. I just did some factoring. So I'm running through and double checking in my head that I factored that correctly. Looking good. Okay, so then we can complete the square. So for the y's, you take half of 10, which is 5, and square that, and you get plus 25. But you're not really adding 25, you're adding 9 times 25. So you're adding 225. And then for the x's, half of 6 is 3, squared is 9, so you add 9. But you're not really adding 9, you're adding a negative 225. So this has a funny way of working out. This one doesn't always work this way, but this one has plus minus the same thing down there. So you end up still with 900. All right, so you got 9 parentheses y minus 5 quantities squared minus 25 parentheses x minus 3 quantities squared equals 900. Then you got to divide the whole thing through by 900. You're going to end up with y minus 5 squared over 100 minus x minus 3 squared over 36 equals 1. And there you go. There's your equation in that standard form. Center here is at 3, 5. Because you got the center is still, the x-coordinate and the y-coordinate. This has a vertical transverse axis. So if you went through and graphed it, this is one of the ones that opens like this. Has your center and foci and all that along that transverse axis. All right, last thing, eccentricity. We covered it before, we'll cover it again. This time for hyperbolas. Eccentricity. So if we apply the definition of eccentricity from the previous section to the hyperbola, we obtain this. Deriving it's beyond our scope right now. So basically it comes down to c over a, because a squared plus b squared equals c squared in a hyperbola. So that's the eccentricity of a hyperbola. And since c is greater than a, our eccentricity is going to be greater than 1. Every hyperbola has an eccentricity greater than 1. The closer to 1, the narrower the hyperbola. The further from 1, the larger the hyperbola. So like you have a situation where hyperbola is super narrow. Here's your foci. E is closer to 1. Let's say your hyperbola are not narrow. Something like this, your E further from 1. So it is telling you a bit about how narrow or how wide your hyperbola is. The bigger your E, the wider your hyperbola. And the further away from your hyperbola, you'll see your foci. Okay, so let's say they give you y squared over 100 minus x squared over 81 equals 1. And they want E. They want the eccentricity. Eccentricity is pretty straightforward. C over A. Okay, from this one we know A is 10, B is 9, based on the formula. So we can work with that. Then we know that c squared equals a squared plus b squared for this one. So c squared equals 100 plus 81, which is 181. So do the square root. And that's approximate. And then your e is going to be that square root of 181 over the a, which is 10. So that's going to be about 1.3. They ask us to round to the nearest 10th place. Now they could ask you to go the other direction, and they could give you something about eccentricity and say, use this and write the equation. That's a fun time too. All right, let's say you know the eccentricity is 3. And let's say you know the foci are at -2, 5, and -2, -3. Okay, so if the eccentricity is 3, then c over a is 3. So we'll work with that in a minute. But let's think about where the center would be. Say -2, 5. So focus there, and -2, -3. So we have a focus right there. So the center is going to be halfway between those. This has a vertical transverse axis because the foci are along a vertical line there. So that tells us too about the equation. The y's are going to come before the y's are going to come first, and the x is second on the equation. So our equation is going to be something with y minus something squared over plus x something squared over equals 1. Since our center is halfway between, let's see, we know that our x coordinate is -2, so minus -2 becomes +2. And then our y coordinate, we've got what, 1, 2, 3, 4, 5, 6, 7, 8 units. So 1, 2, 3, 4 units is halfway in between. 3, 4, 1, 2, 3, 4. So our center is there at -2, 1. So y minus 1 squared. Okay, then what? Well, this tells us then about our a as well. Because if it's 4 units like that, a is 4. That's this right here, or this right here. Oh, no, it doesn't tell us that. Shoot. Because that was C. All right, scratch that. Okay, going back. That was C, not B. Sorry. So we can't use that. But what can we use? Oh, we know C is 4 then. Huh. So we can still use this. All right. We know C is 4. So we know then for the eccentricity, 4 over A equals 3, which then tells us that A must be 4/3. That's not very pretty, is it? So 4/3 squared is 16 over 9, so that's going to go right here. The equation. And then for A squared plus B squared equals C squared, 16/9 plus B squared equals 16. So 16 is the same thing as what? 144 over 9. So B squared equals 128 over 9. So the 128 over 9 has to go here. All right, moving along. Then we can clean that up a little bit because of that fraction. I mean, that's in that standard form, but usually, we can leave it like that. Or we can take those 9s and flip them up to the numerators. Oh, I shouldn't have had a plus sign there. I just caught that mistake too. Woo. Minus. There we go. Sorry, that should be a minus in an equation. All right. So we've got the 16 over 9, 28 over 9. Yeah, we could write it also as 9 times y minus 1 squared over 16 minus 9 times x plus 2 squared over 128 equals 1. So that we could do that too. All right, there you go. So either one of those would be acceptable ways to write the equation. All right, well, thank you for joining me for Hyperbolas. I plan on making one more video to kind of summarize everything, wrap it up, but this is the meat of it. You've now seen all the different conic sections that you need to worry about for this course. So thank you for joining me, and I hope to see you again soon, or talk to you again soon.